everybody. Welcome to this week's episode of the SilentPunt Podcast. I'm your host, Henny Hiemenz. A little bit different this week. We're doing a really fun and cool interview with physics professor, world-renowned physics professor, Dr. Gabe Spalding from Illinois Wesleyan University. We talk about a lot of really cool things: space-time, black holes, the multiverse, quantum entanglement, and he takes my dumb brain through it all and teaches me a little bit better than that Neil deGrasse Tyson guy could. Two quick stories that he and I spoke about off air after we finished the interview will illustrate, I think, why he and Illinois Wesleyan play such a huge role in physics really throughout the world. The first is a Illinois Wesleyan student, Henry Philippe, who was heading home on a train back in the early 40s to Chicago, that's where he was from, and happened to be sitting directly next to a man named Enrico Fermi. Really chance opportunity. If you don't know who Fermi is, he's considered the architect of the nuclear age, and he was on his way to Chicago to create the first nuclear pile for what would become the Manhattan Project and Fat Man and Little Boy. Anyway, through that chance encounter, he became a huge part of the nuclear age. A couple years older than him at Illinois Wesleyan was a man named Roger Rasmussen. He was involved a little bit further along in that nuclear age, specifically with the Manhattan Project, and was one of only 8 physicists on site for the Trinity test. If you're aware of what the Trinity test was, it was the first nuclear bomb that was exploded by America that kind of created the nuclear age. He stayed with Los Alamos out there in New Mexico where they did it for a large part of his career after that, and that was all thanks to someone you might have heard of, Robert Oppenheimer, who recommended him. So just an amazing lineage of physics throughout that community at Illinois Wesleyan, and I'm really excited to share this interview with you. And in talking about those stories this morning, it reminded me of something that I announced in our newsletter last week, which is the book that I am writing on John Matuszak. If you don't recognize that name, you might recognize him as Sloth from the Goonies movie back in the day, but he was an amazing football player as well in the NFL, and his story is really one kind of similar to what I was just talking about those two men. Just an interesting thing after an interesting thing after an interesting thing, but also with some tragedy in there as well. Anyway, if you listen to this thing anywhere, please subscribe to my newsletter. I'm trying to build an audience so that eventually I can get that book published. And if it sounds interesting to you, maybe you can read it someday. All right, without further ado, Dr. Gabe Spalding. All right, we are here with Gabe Spalding, physics professor at Illinois Wesleyan University. I will say this is one of the few shirts that I still have from 20 some odd years ago coaching there. It looks like I'm not dressed up, but that's why. It's the one thing I could find.
It's looking good.
Well, thanks for joining us. Like I said in the intro, Gabe is the physics professor, WashU undergrad, native of Louisville, Kentucky, Harvard PhD, and have been teaching at Wesleyan now for a couple decades.
A
couple, okay. The first thing I'm going to ask you is, you completed your PhD in 1990, and it looked like you did a lot of research in nanotechnology and quantum stuff. I was 15 years old at 1990. I don't think I'd ever even heard of the word quantum before. What did research in quantum physics look like in 1990 or thereabouts?
Well, all of my PhD work was supported by the military. My PhD thesis is a report to the Office of Naval Research. And they wanted to be able to detect submarines. This was an important thing for national security. And that's not an easy measurement, so you have to go to extremes. And eventually some of the things I made went up into satellites. Again, you're looking, when you fly over a rogue state, for things that might be dangerous to us. And when you have a camera that's way far away, these are extreme measurements. So that's what it was all about. Going to extremes in what can we see? What can we detect? And that involved nanotechnology, and it involved extreme states of matter like superconductivity. And it was a good start. A lot of those things are still important today and are leading to an economic explosion with quantum right now.
Well, that's how we our first conversation happened, I think, was talking about some of the things that are going on now with that. And you very politely tried to explain to my dumb brain kind of how some of that stuff works in an iPhone and the camera now. Can you take our audience through that a little bit?
Sure. Well, here is a phone that it's an Apple phone, and on the camera side, there's a lens, there's a flash, and between there's a really tiny little dot. And that really tiny little dot on this model is a single photon detector. What happens is the flash sends out an infrared pulse, and it's got fast enough electronics that it's timing the first photons to come back. At the speed of light, it doesn't take long for light to go out and hit the first thing that it wants to focus on, whoever you're aiming your camera at, and come back. But those little detectors, they're made at a foundry in Edinburgh.
Did you say Edinburgh?
In Edinburgh in Scotland, yeah. And so I collaborated with a professor of electrical engineering at University of Edinburgh, and we ended up working with arrays of these to make cameras that can almost have effectively 1 trillion frames per second. And at that point you're saying, whoa, this is a whole new world. We keep seeing our students are taking us to new places. And right now the students here are working on things using, in fact, much better versions of those detectors to make measurements that have a lot of impact. For example, can lower how much X-rays a patient will need in a hospital in order to make a medical image. That's a very good thing because X-rays can do damage.
Right.
If you have a high dose, that's bad. If you can lower it and lower it a lot, that's a big deal. And that's quantum measurement.
I had a question, but then I guess I don't even know, like, how do X-rays relate to that? I would think that's like a completely different thing.
X-rays are light. They're just light with a very high energy. So each little bit of light, the energy comes in little lumps we call photons. And if those lumps carry a whole lot of energy, you might call those X-rays. Visible light, those lumps don't carry that much energy.
Well, it does go into my first kind of question in the lightning round of photons, and I've read a handful of times about the double-slit experiment and photons and quantum physics. Can you again explain it to me like I'm 5, what the double-slit experiment is and teaches us?
Well, the most widely used upper-level textbook on quantum is mostly theoretical. It doesn't cite very many experiments, but it cites mine on the double-slit experiment.
Really?
Yes, and we did it in a strange way. We had Blu-ray lasers. You remember Blu-ray was sort of like DVD, a way to record information. These are blue lasers. So each photon has a little bit more energy than normal light. We send them through a transparent crystal. So most of the light just goes right through because it's transparent. But in this weird crystal, an occasional photon, we name her Hermione. She gives up her energy to two photons. We name them Harry and Ron. And Harry and Ron are inseparable. In the language of science, we say they're quantum mechanically entangled. Whatever Hermione's energy is, that's the energy that they have in total. If Hermione was heading straight down towards you, well, then if Harry's heading a little bit that way, Ron has to be heading a little bit that way. So it all adds up to the momentum that Hermione had. Down where Harry's going, we put two slits. Down where Ron's going, we put a camera. We're going to make an image of the slits using light that has never interacted with the slits at all. And this is actually how we're going to lower the X-ray dose in the hospitals. Remember, if Harry's going a little bit this way, Ron has to be going a little bit that way. So it all adds up. If Harry's going a little bit too far and misses the slits, hits the walls, not the openings. On the far side, we have one big bucket detector. And we don't detect Harry. But if Harry makes it through the slit, we're going to use that bucket detector to turn on our camera. And because of this correlation between Harry and Ron, we're going to see the slits. If we go downstream, we move the camera further away, we're going to see a pattern called an interference pattern that can be mathematically described as it had to go through both slits at the same time. Except we did it with photons that never even saw the slits. And so what it tells you is that there are correlations, and if you try to tell stories about here's exactly what happened, you can get confused. All that's really happening is that we have correlations that are required by the conservation laws. Conservation of momentum was the key, conservation of energy was important, and it leads to these correlations. People tied themselves in knots trying to say, hey, how can you have one little lump, one electron, one photon, one whatever, that goes through both slits, because you'll never find half an electron. It's something that builds up in these correlations. The correlations can only be described in a way that is as if the thing went through both. It gets weirder, but that may be enough. The bottom line is you tie yourself in knots if you try to tell stories pretending that electrons or photons or atoms are little balls. They're not really.
That leads to my next thing, but before I get there, and your answer may have already spoke to this, but I may have missed it. One of the things about that experiment that intrigues me is how they behave differently if they're observed or not observed.
Well, yes, there too, people have tied themselves in knots trying to explain it as if things were little balls that they're not quite. And really the framework that we have for describing all this stuff is what we call probability waves. It's a little bit like if you were a city manager controlling resources like the police department and so on, and there were a crime wave sweeping across the city. Well, that could be useful to you in allocating resources. You kind of know, oh, there's something going on that's sweeping across the west side. We should put more resources over there. But a crime hasn't occurred when you're just looking at the statistics. A crime happens somewhere, sometime. And before it happens, it doesn't have a place. It doesn't have a location. And that's what freaks people out when we start talking about electrons and phonons and photons and all these different things, that before we detect them, they don't really have a place or a time or a trajectory. And if you start to describe them that way, you get nonsense. It's really just a statistical framework, like that crime wave.
I'm going to read a quote from your teaching website that I think speaks to what you're talking about, because I've just recently, maybe in the last year or two, started to read about that and learn about it. And it's vastly different than my 10th grade science class that I learned. But you said, in teaching, I have to work hard to convince students that there really isn't anything orbiting in the stationary states that we can find in solving the Schrodinger equation for the hydrogen atom. That's kind of getting at what you're talking about in terms of like the nucleus and the electrons and how we were taught.
Yes, we lie to school children. we give school children what you might call a minimum viable model. It's as simple as possible so they can make some progress. And so it's a little unfair when you start learning in grade school and high school about these things. They do treat electrons like little blue balls because you get a kind of sort of wave forward. And it gets you somewhere, but it's not a very accurate picture. And so people are stuck with these pictures from high school that they have to unlearn.
When they get to you.
Yeah, if you stick with those pictures, you're leaving money on the table. If you start to say, no, they have this statistical wave that we can use, that means there are correlations here and there in space and time, and that's money. Correlations are things you can exploit in order to do engineering.
And what you were describing a moment ago is that I didn't have this in my notes, but I've heard of superposition before. Is that what you're talking about with those particles?
So it's a little bit more than superposition. It's called entanglement. But yeah, that's the right kind of notion. They're displaying what Einstein would have called quantum weirdness, or spooky action at a distance. And because of his phrase, spooky action at a distance, we call what we did ghost imaging. We're not imaging any paranormal things, but Einstein called it spooky, and so it's just a play on that phrase.
Well, it's spooky because it doesn't, I'm going to struggle finding the words, but they don't act the way you would expect them to act.
Well, that's because you're stuck with these notions from high school about little balls moving along, and you can't really get away with that. It's kind of true that engineering up until not that long ago limited itself by assuming that the energy comes in lumps, and so this would be the ultimate limit of every engineering measurement. Is called shot noise, where you're getting these energy coming in lumps, which would be electrons in an electric signal or photons in an optical signal. And everybody thought that was the end. And it turns out, nope, we can do a lot better if we recognize that those stories from high school aren't quite the whole story. And that's the revolution that's leading to billions of dollars coming to our state right now. We say, oops, we left money on the table.
What do you mean by coming to your state right now? Wesleyan's in Illinois. I assume you're speaking of something specific.
So there's the Illinois Quantum and Microelectronics Center, which is going to replace where U.S. Steel used to be in Chicago. It's a big tract of land that was not really being used because U.S. Steel had moved away a long time ago. And the state put some money in. Chicago was able to say, here is this land, we want it developed. And they have really found a lot of big takers. So there's been investment. And the investment now is in tens of billions of dollars. And suddenly, we're finding all kinds of internships for our students that are just going through the roof. Even our first year students, this past year, 37% of them had paid internships
That's
in
fresh.
the summer. Good paying. And, historically, freshmen, often they just want to go home. They're not necessarily even looking for a paid internship. And the money is just flowing to them right now. In particular, because we teach the quantum things right away. So these first-year students have something that is in high demand right now.
That down my list was to ask you about quantum computing, but I think this is probably a good time to ask about it, because it seems like a really difficult thing where the smartest people in the world that are doing this work still have huge questions about exactly how everything works, but we're building these machines that actually do stuff. That disconnect for me is hard to wrap my head around.
So back in the 1960s, there was this moonshot effort that our society said we're going to put a whole lot of smart people to work and we're going to do something aspirational. We're going to push the boundaries of things beyond what we've done. And there were all sorts of technologies that came out of that effort. When you put smart people together and say, go, 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 push the boundaries as far as you can. Everybody push in this direction. Interesting things happen. And the quantum computing, we're already seeing that there are technologies that right away can be applied. Even if, man, there are a lot of interesting questions out there.
Some like secondary things that are coming out. I'm looking for this, but we've figured this part out.
Left and right. It's happening left and right. And so it was really great that Illinois chose to make this investment. Last summer, I went to the Global Physics Summit. This is 17,000 physicists from around the globe getting together. And there's a major trade show that happens with that. High-end equipment, technologies that are being developed. And a lot of it in this year's show had to do with quantum computing and the efforts people are making and the things they're already building. There was only one state represented, Illinois. There were countries represented, only one state.
That's pretty cool.
Yeah.
Another thing I had on my list that I think this transitions nicely into, because of my very minimal understanding, if one of the reasons quantum computing should work maybe leads to the belief or understanding that there is the multiverse, that they're pulling from all these different possible scenarios. I'm probably saying that really dumb, but I think you probably get where I'm coming from.
So, yeah, as people talk about multiverse, and sometimes people try to, in explaining the physics, they start sounding pretty weird. But I'll remind you, the point of physics is not to sound weird. The whole point of physics is sense making.
Understand.
It really is, how do we have operational models that allow us to do things, allow us to predict things that are real, allow us to make things that work. So when people talk about the multiverse, they're trying to understand, in a way, some things that are hard to put into the language of common experience. I think I'll leave it at that. It gets into philosophy, where what we have are these models that work for making things. Interpreting them is a little bit open to debate.
And having the words to explain is challenging, I would imagine.
Sometimes.
You seem like you were going to say something else.
Well, I think that it's not bad to go back to what I said before, where I made this analogy to a crime wave, to an operational model that has some utility. I think people get in trouble when they start to think it's about truth. You know, I can say the door to my office is a rectangular door. You know, there's no such thing as a rectangular door. If you look at it closely enough, it's got to be different. If I look at you, you're not really well defined. There are atoms adsorbing, atoms leaving you. You're kind of, But you know, all we really need are models that have operational utility. We don't need truth.
Yeah.
And I don't think that science ever could give us truth. Truth is inaccessible. Words always cut off something. And I think that's why ultimately people start to make things sound weird, is because they're taking statistical models and they're trying to treat them as though they're something different than that. They're just not truth. But they're useful.
Getting back to the useful part, a lot of what you're talking about sounds like AI to me, in that there's a lot of money being put into it and research, and this is amazing and we're learning so much. But also, you mentioned the space race. We knew where the end game was at least hoping to go. The Manhattan Project, you knew where the end game was hoping to go. There may have been ancillary things that we learned because of it. But both of these things, to a lay person, AI and what you're talking about, it seems like the smartest people don't exactly know where we're going, which is maybe disconcerting for normal people.
Well, I think we have a lot of places we want to go and a lot of applications we want to see. And I think what you're really saying is that when you start to talk about it in terms of first principles, what's going on, people disagree. But in terms of, does this mathematical framework give us things that we can do and make and use and have them work, that's not really something that we disagree about. It does work.
Right.
The interpretation is where people tie themselves in knots. But we have a useful turn the crank kind of mathematical framework. We have frameworks mathematically for AI too, and they're improving. Right? The latest AI is not hallucinating the way that the earlier AI was. They're doing tests to validate things. To really advance, so the Department of Energy just to our north, Argonne National Lab, has the world's most powerful AI supercomputer. It's called Aurora. this doesn't exist just in software. You have to have advances in materials. You have to advance the hardware, and that comes out of people doing quantum. All these things fit together. Quantum and AI go together. When you look at Google, they call their effort quantum AI. So if you look at NVIDIA, they see the future of AI as quantum. So it is another approach to architecture for computers and hardware that is going to add to our computational capacity. If you have computational capacity, you can start to do things like develop new drugs, save lives. When we had the pandemic, most people have no idea the role that science played. The way that the Paxlovid vaccine for COVID was developed was at Argonne National Lab, accelerating electrons to very near the speed of light so that they would broadcast very coherent X-rays, about 1 billion times more powerful than what you get in medical X-rays. And those were used to identify protein binding sites and figure out how to develop the vaccine. There's a lot of science that you can't do without, that depends upon people advancing our computational capacity. We can't right now go back to a simple agrarian life. There's no way. We depend upon this interconnected scientific and technological economy. And you should feel good about the fact that our nation wants to support science. Science has been good to us, science. So,
That's good.
that's good.
I should hope so. So you talked about the Argonne National Lab, and one of the things that you mentioned sounded a little bit like what I've heard the Large Hadron Collider does. Are those in any way related? You talked about
They're
smashing things together,
powerful
or yeah.
accelerators. When you get things going very fast, interesting things happen. We actually have a technology here that we've been working on in collaboration with another U.S. Department of Energy lab, Los Alamos, where we're completely revolutionizing antenna technology. And the output, we hope, will be affordable, high-speed internet for people in rural communities. All these weird, extreme scientific things that are way beyond common experience, they do have applications that impact everyday life, right?
Yeah, that I was just reading something in the last week, and it was kind of in relation to some of this stuff, but in things that you can't see and waves that you can't see. And it's like we don't, normal people, we have Wi-Fi and we have Bluetooth and we have all these things that we have no idea what they are, but we can't see them. It's no different than what we're talking about. Super smart people figured out how to use them for humanity's benefit. What Before moving on, can you speak to what you were just talking about in terms of the project at Los Alamos and high-speed internet for people? That I know the problem that you're talking about and how we've talked about it as a country, but that part I'm not familiar with at all.
Well, I'll explain it by analogy. In fact, one of our collaborators from Los Alamos has just retired from Los Alamos and is probably moving here to commercialize things in Illinois. Illinois is very friendly to starting up these things. Her mother worked as an engineer at the time that airplanes were passing through the sound barrier. And at that time, we didn't know enough about how the drag builds up as you go faster and faster. And because we didn't know enough, there was a gap in our knowledge, some test pilots lost their lives. But eventually we figured things out, and humanity could go through, Chuck Yeager and others, go past the sound barrier. And you all maybe are aware of a sonic boom. A sonic boom is where you have this plane going through the air so fast, it perturbs the air, it pushes air, all the sound waves pile up on top of one another. And when it goes past you, boom, it's a big loud sound. Well, that's exactly what we're doing in these new kinds of antennas, is we're getting not a sonic boom, but a photonic boom. We're getting an electromagnetic pileup, and it's very directed, and because it's so directed, it can reach rural people very efficiently. So
That's really cool.
it's fun.
That's amazing. All right. Okay. You're super smart. You're a quantum person. You have to like space.
Sure.
What, explain in, again, like we're five, what a black hole is.
Well, where to begin, right? The thing is, you kind of have to know a little bit about Einstein's theory of relativity. And Einstein's theory of relativity starts to, again, when you first say it, sound very weird. That there's no such thing as absolute space. There's no such thing as absolute time. What do you mean by that? We mean that how information flows to a measurement is pretty straightforward, but it means that what you measure, if you're measuring a signal that is a timing signal, is subject to the same rules as anything else. And from that, you start to see that things you assumed to be true are just not. But we have a simpler story from Einstein than kind of what you assumed the way things were. It's just not at all what you assumed. So there's no such thing as absolute space and absolute time. Moreover, if you were in a spaceship far, far away from everything and it was accelerating at 9.8 meters per second squared and you dropped a ball, it would be just like on Earth. You'd feel everything would be the same. There's an equivalence between acceleration and gravitation. When you're near a very, very massive thing, all of these come together to say that you have distorted the fabric of space-time. And that was a weird thing to say. When Einstein said it, kind of nobody believed it. But then there was the eclipse of, was it 1919, when Arthur Eddington went out to prove Einstein right. We know where the stars are. We know the pattern of the constellations. You don't see the stars during the day because there's so much light from the sun that you can't detect those little faint sources. But during the eclipse, you can see them again. And the ones near the sun they appeared to be distorted in their positions. That meant that even light was bent by the gravity of the sun. If you get something more and more and more massive, you get so much bending that if light goes in, it can't make it out. Nothing can make it out. We don't have any chance of a measurement that accesses the beyond the event horizon of a black hole. And there's a lot of weirdness. When we look and try and make measurements, we don't get the normal flow of space and time that you expect. It would seem like things are going slower and slower and slower and we could never see something cross that event horizon. To us, it would appear to stop. These are all weird things, but the truth is we've been looking out in space for a long time and doing measurements. And every measurement we've done has agreed with Einstein's theory, which seems weird, but is actually simpler than maybe your common sense assumptions. I don't know that I did a good job explaining that.
No, you did. And take a step back. What created them in the first place, or creates one in the first place?
So if you have a star, it's a lot of mass, and mass wants to fall in. The only thing holding up a star is the fact that there is all this energy pushing out. And as it uses up its fuel, if there's enough mass, it will just collapse down, eventually a dead star, to the point where you have this huge distortion around it in this fabric of space and time. So a black hole is a collapsed star.
That much I've known for a while. The reason why I wanted to ask you that question is because something I read recently talked about, okay, what happens when a black hole goes away? And that part was confusing, interesting. Explain to us what the expectation is of that when that happens.
So there are some weird processes where a black hole can kind of over time evaporate. Some of the energy that has gone into it can leak out through a special process that Stephen Hawking came up with. And over a long time, you can have something that maybe disappears. We've not exactly seen that, so again, this is very theoretical at this point. And there are a lot of questions that people have, again, looking at just trying to understand some of the basic statistics of how do our laws work when we get into these really extreme situations. And if we can understand those a little better, we'll probably understand our laws a little better. So people use these as toy models, but it's a little beyond what we're able to measure at this point. We're barely at the point where we have measured black holes. We've made direct images of black holes fairly recently.
I was going to say, I'm not sure I'm familiar with that.
Yeah, that was a major breakthrough. They had to really do some extreme measurement because these things are very far away, right? And when things get far away, they're small and hard to resolve. And yet that was a huge success. With enough data, they were able to, over time, accumulate enough information that they could reconstruct an image of what they were looking at and see the blackness in a surrounded bright area. These first images of black holes directly seen, well, we're in a new age of astronomical measurement, but we're nowhere near being able to see a black hole evaporate.
Getting back to how it formed to begin with, you talked about a star collapsing upon itself, and the whole idea in a black hole is you get this, all I know is from science fiction basically, but you get close enough to it and that gravity is pulling things in and it crosses the event horizon, and whatever is past that is then in the event horizon for good. And what is moving on from what I had just asked about, okay, all that information or energy or whatever goes in there, theoretically, it does eventually disappear.
If the black hole evaporates, then
where does that all go?
Is that information radiated out? And
Right.
there are certainly people that say that that's the way it must be, that if you could collect all that information, you could kind of figure out the story that went all the way back to before the thing fell into the black hole. Maybe. That's a hard... it's certainly beyond our capacity to do anything like that. So that is where people are wondering, what are the limits of our models?
This is a much easier question. It's a personal question. So, you got an education, a undergraduate degree, a PhD. We've talked about, lots of different things of how all of this stuff is making money for lots of different people. Why have you chosen to spend your life in a classroom teaching young people about it? Surely you could make a lot more money maybe working for this company or that company. What is it that you love about what you do and why you've chosen to do it?
Well, my wife asked me that question because, the students that I teach can, if they're doing things with the advanced lasers and imaging and some programming, they're starting at over $130,000, over $135,000 with nothing but the bachelor's degree. And I don't make that kind of money. So my wife is saying, how come the students you're teaching are getting paid all this money? Couldn't you get some more money? But I like what I do. And I have this freedom to play. My job, I say, is like improvisational comedy. Each of my students, I want them to go find 4 cool things a week and then come back and talk to me. And my job is to help them connect the dots. My job is to open the door. And this is fun. I get paid to do this. This is a game. This is my Rubik's Cube. By the way, one of our incoming students this year ranked, I think, 12th in the world for solving a 3x3 Rubik's Cube blindfolded.
Oh my gosh.
You've got to see the video of that.
That's insane.
They get to look at it for like 3 seconds and then...
Oh, it's not like they haven't memorized the particular thing. It's like a...
They only get to see it very briefly.
Oh gosh.
And then go. The students that I teach are those kinds of students.
I know.
They are just intellectually, they want to play. And it's fun. So what I build is them. And it's very satisfying.
Well, and you therefore probably have access to so much more knowledge and interest and intrigue than you would if you were in a particular silo making widgets and a lot more money, but intellectually maybe not as stimulating.
Well, I mean, I know that my students do go off in the world and they do good and they have fun doing it. One of my students, he was working for Boeing on something that was Phantom Works. When it's got a name like that, you know he's not allowed to talk about it. And then he went from there to go work for Apple. And he and another of my students developed all the optics behind the Apple Vision Pro. This is their AR, artificial reality, virtual reality headset. And he said, then he really couldn't talk. The secrecy at Apple was more than the secrecy in the Defense Department.
That's very scary.
So I like to talk to people. I like to just be able to go out there and talk to anybody, anywhere, who's open to talking, and chase ideas.
That I was going to wrap up, but that really brings up a question I've thought about before and read about is, the difference between privatizing information and leaving it to academics. Do we leave something on the tape? Yes, all of these companies are driving money and research and all of that, but at the same time, they're not sharing information necessarily the way academics would. surely there's trade-offs, positive and negative. You've been doing this a long time. Have you seen that change in one way or the other?
Well, I'd say the biggest change during my life has been kind of a collapse of real research in industry. There's development, but when I was young, there was Bell Labs, which developed the transistor. Well, the reason they could do that and a zillion other Nobel Prize winning things, a zillion other things that have impacted our health and well-being, was because that was a guaranteed monopoly. And so they could really invest in things. It wasn't that different from having, the federal investment in research. Right now, the administration is wanting to say, well, private industry can do more of the research, but that's a big shift. That just hasn't been what's been happening. There's been a lot of development, but not so much real research, with some exceptions. So I think certainly as a society, we depend upon ongoing innovation, and our economy does benefit. But right now, the way it's worked has been with this open dialogue being a real way to move faster. If things were siloed, I think, a lot of it would be slower.
Yeah, and so everything is Wall Street and making money and profit. So you're not, as a company, going to invest all that much time unless you know for sure, time and money, we're getting XYZ out of that. Does that mean universities are playing maybe an outsized role or a larger role in that than they used to? I mean, somebody has to be picking up slack.
I'd say that really our economy since World War II has been the universities. If you want to have a vibrant economy, you want to have vibrant university systems. That's the way our world has worked. And that's not changed. It's maybe accelerated. I'd say around every university you see this generation of ideas that do get commercialized, that do go out there and make money, and that the investment we've made as a society, a lot of analysis says it's been a very good investment, even if you're just saying from the economic point of view.
Yeah, the economic point of view, the quality of life, our standard of living, that's, people complain a lot about a lot of things, but it is infinitely easier and better to live today than it was.
And that's why there's really this broad bipartisan agreement. Both sides of the aisle say, when they study it, oh yeah, that's a good deal.
Yeah. Let's not go backwards.
No.
Well, Gabe Spalding, Illinois Wesleyan, thanks for joining me.
Good chatting with you.
You as well.
For the Indians, one run on, one hit. That's all. We got one goddamn hit.
You can't say goddamn on the air.
Don't worry, nobody's listening anyway.